Hello, welcome everyone. I started a new repository that is also public on my GitHub page, the oversampling test, and it includes basically some alternative oversampling solution for my juice projects. And you can take a look at it too if you want to. It is basically a standard juice project with the typical stuff when you make a plugin, and it has the parameter header that I always add to all of my plugins, but I won't get into detail about that in this video because it's not very relevant. It has nonlinear DSP header that just has some basic DSP things like a phasor and a sine oscillator and a ring mod, a wave folder, a saturator and a vibrato unit. So basically some nonlinear DSP processors that I can use to test my oversampling capabilities. And then the most important folder, the oversampling folder, which has a so-called latencyHandler, which is used to handle latency of both the oversampling class and the nonlinear DSP processors. It has the general setup of a filter, some utility, and a convolution filter with some interesting properties that I will talk about. And of course, the heart of the oversampling namespace, which is the oversampling processor. I will go into detail how the oversampling is being implemented in the plugin processor header as well as the CPP with processBlock and everything. But before doing that, I will just show you some practical examples. I turned down the volume of this sine wave oscillator completely. It is a script that I wrote in plugin script that just generates a pure sine tone, and I can just put it to different frequencies. At the moment, it's on 1000 Hertz. And the range that we have here goes from 0 to minus 170 decibels. So this is pretty deep, and if there is even some very slight aliasing, then you would see it. For example, if you would take the sine oscillator that is built in Serum now, then you would already see some spikes here because it's wavetable based. Now when I turn on saturation, then of course I get some harmonics into this thing, and I also get some other things which are supposedly aliasing artifacts, and I can turn it up, and what this does is it makes everything louder, the actual harmonics as well as the artifacts. And when I turn on oversampling, I get much less artifacts, and the ones that are still there are lower in volume, but they're not completely gone. Like here's one even below the fundamental frequency, which often sounds not very nice, at minus 60 decibels, and here's one at also something like minus 60. It could be better for sure, but on the other hand, there were just tons of little spikes here and they were all gone, so that's pretty cool. Now the wave folder. A wave folder is something that does this to a wave. And yeah, it's just wave folding. So it basically creates a bunch of crazy harmonics, crazier than saturation, and it's not easy to tell which of these are harmonics that are kind of to be expected with wave folding and which are artifacts that I can get rid of by oversampling, but we will find out now. So basically it's the same situation as with the saturation. We just lose a lot of these spikes and it looks much more cleaned up. But still, our frequency is at 1000 Hertz and we get a lot of stuff below 1000 Hertz. I gotta say, it is kind of harmonic because let's see, we have 200 Hertz and we have 600 Hertz or so. It's nothing strange, like, you know, 132 Hertz or so. It seems kind of related to these 1000 Hertz in some weird way. What do we have down here? 400 Hertz. So you see all the spikes, no matter if they are high or low in value, they kind of make sense. Now, next thing we try, which I find most important for my personal plugins, is the vibrato. We have vibrato with the vibrato depth. And yeah, the vibrato depth basically, well, it's not easy to tell what it does because it's different for different frequencies, to be honest. One thing that can be said for sure is that the frequency makes this thing wider, obviously, because the frequency is shifting around very quickly here, and then it looks like we are on multiple frequencies at the same time. Only if we turn down the frequency a lot, we can actually see that it's a vibrato and not something else. So let's consider a fairly strong vibrato and fairly much depth, which should be the case here. Let's listen. Yeah, that's pretty strong. What do we have? We have minus 90 decibels of just random noise all over the spectrum, and it has these little dips and valleys here where it goes down to minus 140, but it starts at minus 80 or something. The difference between the noise floor and this thing is definitely not cool yet. We can improve that. And we see the noise floor dropped considerably to minus 120 decibels. Here we have minus 113. So basically this just looks much nicer. Also, there are bigger gaps between these artifact harmonics than without. There's just complete noise all over the place, and now it kind of looks tidied up. So the oversampling definitely already does something good. One other thing to note before we go to the code. You might have noticed that there is a dip in frequencies at the end of the spectrum, which is, I know for sure that it starts at 19 kilohertz. So at 19 kilohertz, things just drop until they reach Nyquist. And I'm not sure yet if I should keep it like that, because it might look a little bit unprofessional to some audio engineers, because they might think they can hear 19 kilohertz and then they want to not lose these upper frequencies. I'm not sure how to realize that yet, that it is like that. But since it does not make an audible difference, I will just keep it like that for now. And I think that's okay. I want to show you how this stuff sounds on a beat so that you can get a better idea on the quality of everything. So I don't know about what you think, but I feel like all of these DSP processors sounded much smoother with oversampling enabled, even though this is definitely not the perfect oversampling, the most perfect oversampling that you could think of. But I'm also not a DSP expert, so I'm already pretty proud of this. Now in the code we start with what's going on in pluginProcessor, because the most interesting thing is how it is implemented. So we have a latency processor oversampling our DSP classes, audio processor value tree state for the parameters and the parameter pointers themselves. We instantiate all of the stuff. The latency processor needs to know about the processor. The oversampling class needs to know about the channels and also about the latency processes. The DSP things, I have implemented them in a way that they don't need anything. And the parameters, well, they do the typical parameter stuff. At the beginning, one has to make sure that all of the DSP classes that would change in their properties have an oversampling listener, or they should be more like registered as an oversampling listener. So they should inherit from oversampling processor listener, so that oversampling can add this listener to its vector of listeners, so that if the oversampling thing changes in some way, then it can send a message to all the DSP processors and they will change their stuff too. The latency processor has the concept of inducers. The vibrato is a latency inducer because it can induce a different latency due to the size of its buffer, and the oversampling class as well, but I add it as an inducer somewhere else. Now the prepareToPlay method now works like this. Basically basically just as before, but the difference is that instead of using sample rate and samples per block directly, we first call prepareToPlay on the oversampling class, and then we get the new sample rate and samples per block from that and can feed our DSP processors with these values. Now in processBlock, it's actually quite easy. First of all, the basic stuff that is always in processBlock, then we are upsampling with oversampling and returning if reallocation has happened, since that is not cool in the audio thread. And then some nonlinear processing happens on the upsampled buffer. And at the end, we are downsampling the oversampling again into the original buffer. And then I'm applying gain, which does not need to have oversampling in it. Okay, so first of all, just get this out of the way, the latency handler, because it's pretty easy. Well, it is a processor and it has a timer. The timer is set to 1000, so it's quite slow. And well, you can add inducers to it, latency inducers, which are defined up here. In its timer callback, it goes through all the inducers. And if any of the inducer wants to make an update because its latency has been updated, then we return with the function update, which sets the latency samples of the latency processor to 0 and then adds all the inducers latency samples to the global latency samples and sets their latency updated to false, so that next time the timer callback is called, update will not be called again. We also give every inducer the maximum latency number, and only then we tell the audio processor that there is a new latency. So as you can probably imagine, this little structure enables me to just define a lot of the DSP classes and stuff as latency inducers, and then this thing will just automatically handle sending in new latency samples if needed. An inducer is just something that a DSP class can inherit from, and it, as you've seen, it has latency samples, latency all, and latency updated. Now the oversampling class, the processor has a listener, so everything that is able to listen to oversampling must have an update oversampling method where it gets a new sample rate, block size, num channels, latency and stuff like that. The processor itself has the old data from prepareToPlay. It has a buffer for upsampling. It has a bunch of filters for 2x, 4x upsampling, 4x, 2x downsampling. It has the new data of the sample rate and block size. It has some utility stuff for setting it enabled and disabled. It has a vector of listeners. It has a reference to the latency processor, and it has some utility variables for the different num samples of the different stages of the filters and stuff. When a new processor is made, a little function is called on the filters, which basically gives them some default coefficients to work with, and they are tuned for a 44-100 kilohertz sample rate, because that is the most critical one, where the initial filter has to be the steepest. And if the user uses a higher sample rate, then this oversampling class, which is still kind of naive, would still use a steep filter, and I have to change that at some point, but not now. We're adding the oversampling class to the latency processor as an inducer, and we set update the latency, which basically just means getting the latency from all of the filters, and then that's the latency of the processor. In prepareToPlay, we just get the current normal sample rate and block size, and if the oversampling is currently enabled, then the new upsampled data must be multiplied with the current order, which can only be the maximum order. At some point I want to make this more flexible, but not now, and else it is just the same. Then we resize the buffer to block size times max order, so that we never have to resize it later in processBlock, obviously. And we also update the latency. Now, our upsample method is the most interesting thing. If the oversampling class wants to update at this point, because maybe the user pressed on the update button, then we are storing the temporary enabled variable into enabled, so that later when we reach this part of the code, different stuff could happen. Then we call prepareToPlay with the normal sample rate and block size. As you know, depending on if enabled is now true or false, different stuff will happen. And then we go through all the listeners and call their update oversampling method, so that they can update their stuff as well. And this is the point where a lot of buffer reallocation can happen and will happen. Then we set one update to false, so that next time this is called, this is not be done again, and we return null pointer. And as you've seen in the processBlock method, when null pointer is returned, then we know that some reallocation happened, so we go out of processBlock. If something is enabled, then a lot of fun stuff happens, and else we just return the non-upsampled input buffer, because obviously it's not enabled. If enabled, we kind of get the whole num sampled stuff, and then we resize the buffer to num samples for x, which is a smaller number than the whole size of the buffer. But since we use true false true at the end, it will not reallocate any space or so. It will just stay in place. But the cool thing is that they implemented the juice audio buffer in a way that it will just give different num samples than its actual allocated memory in the end. I think that's the same principle that they use with the audio buffer that is being fed forward to processBlock, which is kind of neat. One of the reasons why I made my own oversampling class and did not use the one in Juice is because they did not use audio buffer in their DSP oversampling class, but they used audio block. And that's the kind of reason why I want to use audio buffer, because it has functions like this. So then we get the samples for upsampling and the samples that went into this method, and we are applying zero stuffing and the 2x filter in a channel and sample loop, just like this. There is a filter, and the filter has a method for processing a sample up if it's even, if S is even, or if S is odd. With zero stuffing, every second sample is just zero, so we can have some optimizations in our filter class as well. Now basically the same thing happens for the 4x filter, but I had to phrase it a little bit differently, like with a backwards loop and with a filter block processed after this kind of stuff, because I'm not sure if there is a better way to do it. At the end I return the buffer, which is the member variable of this class, and then later in the downsample method it's even easier. I'm just getting the samples up and out, and then I apply the downsampling filter, downsample this thing, apply the downsampling filter for 2x, and downsample that thing. So that is really as easy as it can get. There are some utility functions in here for getting information that can be displayed on a screen or something. setEnabled might be a little bit interesting because it works like this. If the thing already wants to update, then we cannot successfully change its enabled state again, and that should prevent the user from making too quick changes accidentally. Enabled temp is being set to the new enabled state if this was successful, and then we can set one update to true. The next processBlock caller will jump in here and see one update is true, and then we'll do all the stuff, and then we return true because it was successful. Okay, so that's basically how the oversampling works. I could also go a little bit into detail about the filters, but I don't want to do that too much, because all I did basically was just going to dspguide.com and doing the lessons from this book about Windows Sync fear filters, and I have made another video where I was talking about this journey already. I think it's one of the PNS repository videos. I have a class for impulse responses, which is basically just a wrapper around the vector float data and a latency information. A make sinc filter static method, which returns an impulse response. You give it the sample rate, the cutoff frequency, and the bandwidth, which is how long it takes until it's stop band, where the spectrum is 0, and then also the information if it's upsampling or not, because there was some optimization about the target gain here. The upsampling filters need a target gain of 2 and the other one's 1 anyway. So it basically checks if the arguments were invalid, because that might happen, because the cutoff and bandwidth together should not go over Nyquist, and the things by themselves should also not go over Nyquist. If they do, then I just return an impulse response that just has the number 1 in it, which means that it will not change anything about the audio. This case will not happen anyway if the coefficients are not set by the user, but actually by me. Then there is some utility information about the arguments from the method. Then there is a lambda about the sinc function, the lambda about the black man window function, which you can read about on that webpage that I showed. A vector for the impulse response, which just has n samples, and each sample of that is sinc function times black man window of n, and then I'm normalizing everything so that the sum of all the samples in the impulse response is either 2 or 1, depending on whether or not it's upsampling, and I return this thing. Then there is a convolution class, which is basically a single buffer, a ring buffer, and it has the same size as the impulse response. It has some methods like processBlock, where it just does convolution. processBlock up, as I said, can have some optimizations for whether or not it's even or odd. And oh, that even rhymed nicely. Nice. And yeah, I mean, you could watch these optimizations and try to think about them yourself. I will just quickly show you that was even and this is odd. But I will not talk about that. Convolution filter, that's basically just a vector of filters because channel count and everything, and has an impulse response. And I found that necessary to have this separated from the convolution itself, because both of the channels use the same impulse response, but they should not have their own impulse response object because it's enough to have one of them. This convolution filter basically also has all these processBlock and processSampleUp even and odd methods. Alright, so basically this is my oversampling class. I will also keep on working on this project and sometimes give updates and stuff. I want to use it for my own project, so I do have a benefit from this growing over time. I want to try different things like using polyphase IIR filters, but the thing is I still have to learn normal infinite impulse response filter design before I go fancy with this. So I decided to just start with normal convolution infinite impulse response filters for now. And I don't know, I also mentioned some other stuff that I want to try with my oversampling class throughout this video already. So let's just keep this conclusion nice and short. This is my oversampling class, check it out, and check it out later when it's even better.